Welcome back to another video of Solid Earth. Today we're going to be talking about major volcanic eruptions, major tsunamis, natural disaster responses, earthquakes, and mountains. So for both volcanic eruptions and tsunamis in history, I'm going to be giving 6 that I find most interesting or most destructive. So first we have the famous Mount Vesuvius in Italy AD 79, which killed the town of Pompeii. The most recent eruption was in 1944, but it wasn't very notable. There were 3,360 casualties in AD 79 by pyroclastic flow. This is the falling of ash that killed everybody. There was no time to respond, and therefore the entire city was preserved. Next, we have Mount St. Helens in America in 1980. This wasn't very big compared to the other volcanic eruptions, but it was in the United States. There were 57 casualties by asphyxiation from ash. This basically means they could not breathe because the air is toxic. Next, we have the most destructive volcanic eruption to date. This is in Tambora, Indonesia in 1815. 92,000 died by starvation, and several others were preserved by the ash. This is one of Indonesia's 100 plus active volcanoes, and it harmed the growth of crops, and people were unable to sustain themselves. So in the following slide, we have the next 3 most destructive volcanic eruptions. First, we have Nevado de Ruiz in Colombia in 1985, and there are 25,000 casualties by mud flow. A mixture of mud, ash, and water raced down the volcano's slope, the river channels, and almost buried the entire town. Next, we have Mount Pelée in Saint-Pierre in 1902, with 30,000 casualties by pyroclastic flow. This is similar to Mount Vesuvius, where hot ash falls down from the sky and it buries the people. Then we have Krakatoa in Indonesia, 1883. This volcanic eruption caused a tsunami, and the tsunami was a major cause of death, with a total of 36,000. There were a series of extremely violent explosions over the next few months, and the biggest could be heard more than 2,000 miles away in Australia. Then we have the major tsunamis. This is in order of greatest to least. With the top 6 highest magnitudes in history. First, we have Sumatra in Indonesia in December 2004. This tsunami was caused by a 9.1 magnitude earthquake off the coast of Sumatra. We remember from the previous videos that a 9.1 on a Richter scale is pretty high. This caused a tsunami as tall as 50 meters, reaching 5 kilometers inland near Sumatra, and a total of 230,000 people were reported dead. Next, we have the North Pacific coast of Japan in March 2011. We have to remember that Japan is a peninsula and covered on all sides by water, so when a 9.0 magnitude earthquake spawns a tsunami, most of the coast of Japan is covered, and the tsunami was about 800 kilometers per hour with 10-meter high winds, and kills 18,000 people, which is a lot for a small country like Japan. Next, we have Portugal in November 1755. A magnitude of 8.5 causes 3 waves to strike towards various towns along the west coast of Portugal and southern Spain, up to 30 meters high. Next, we have Krakatoa, Indonesia in August 1883. If you remember from the previous slide, there was a volcano eruption, and that caused this tsunami. Waves as high as 37 meters were recorded, and this killed about 40,000 people in total. Next is the Inshunada Sea in Japan in September 1498. There was an earthquake of a magnitude of 8.3, which caused a tsunami, and a total of 31,000 people killed. Next, we have Nankaido, Japan in October 1707. An earthquake of similar magnitude of 8.4 caused sea waves as high as 25 meters to hit the Pacific coast, and a total of 30,000 buildings and 30,000 people were damaged and killed. So we're going to talk about earthquake propagation through different media. This basically talks about how earthquake waves travel through different types of material. We have 2 types of waves. We have body waves and we have surface waves. We're going to first talk about body waves. They travel through the interior of the earth and they arrive before surface waves. They are higher frequency and do not cause as much damage. There are 2 types of body waves. We have the P wave and we have the S wave. P wave is short for the primary wave. This is the fastest seismic wave and the first to arrive at a seismic station or a spot. The P wave can travel through solid rock and fluid like water or the liquid layers of the earth and pushes and pulls the rocks just as sound waves push and pull the air. The second type of wave is an S wave, or a secondary wave. This wave is the wave you feel in an earthquake. An S wave is slower than a P wave and can only move through solid rock. The S wave is what leads seismologists to conclude that the Earth's outer core is a liquid, because S waves move particles up and down or side to side, or perpendicular to the wave direction. Next, we have the surface waves. These waves only travel through the crust, and they are lower frequency and are easily distinguished on a seismograph as a result. Though they arrive off their body waves, it's the surface waves that cause the most damage and destruction. This damage and strength of the surface wave are reduced in deeper earthquakes. So when the center of the earthquake is deeper in the crust, their surface waves are weaker. And as a result, the destruction is weaker. So we have two types of surface waves. The first kind of wave is called a love wave. It is the fastest surface wave and moves the ground from side to side, and it is entirely horizontal. The next type of wave is the Rayleigh wave, named for John William Strutt and Lord Rayleigh, but basically it rolls along the ground, just like a wave across an ocean or a lake through the ripples, right? Because it rolls, it also moves the ground up and down and side to side, and most of the shaking felt from the earthquake is due to the Rayleigh waves. So next, we're going to talk about the epicenter, the surface center of where the earthquake begins. So if you look at the picture, we have the focus of the earthquake, which is on the line of the fault, and that's where the rupture begins. And directly above it, you see this dotted line. That's where the epicenter hits. In most earthquakes, the epicenter is where most damage takes place. So how do we find the epicenter of an earthquake? We use triangulation. Triangulation is a fairly simple method. So for each circle and dot, that's where the calculated distance from each seismometer where an earthquake is shown. The location for where all of the circles intersect is where the epicenter is. So next, we're going to talk about observational techniques. A question for thought. When an earthquake occurs, one of the first questions is, where was it? Why is that? I'm going to give you 20 seconds to think about it. Basically, the location of the earthquake will tell us what fault it was on and where the damage is most likely to occur. Unfortunately, Earth is not transparent, and we can't just see the photograph or the earthquake disturbance like meteorologists can predict clouds. So when an earthquake occurs, it generates an expanding wave from the earthquake. We then observe this earthquake, the network of seismometers on the Earth's surface, as we mentioned before. The ground motion at each seismometer is amplified and recorded electronically at a central recording site. So it might be like a station. If you look at the picture on the right, we have a yellow graph. You don't have to understand how these work, except for the fact that they record the waves, and there is 6 of them, 6 distinctive waves. These are from 6 different measurements of 6 different locations. And using this, we can determine where and when the wavefront passes each station. The procedure is simple. To guess a location, an origin time, and a depth, and compare the predicted arrival times of the wave from the guessed location with the observed times of each station. Then move from one station to the next until you get one that reduces the difference between the observed and calculated times. So we have 3 major locations for earthquake zones. We have the Ring of Fire, we have the Alpine earthquake belt, and the Mid-Atlantic Ridge. So the world's greatest earthquake belt is the Circum-Pacific Seismic Belt, or the Ring of Fire. So the Ring of Fire is the world's greatest earthquake belt. It's also known officially as the Circum-Pacific Seismic Belt, and it's found along the rim of the Pacific Ocean, which is where 81% of the planet's earthquakes occur. And a question for thought again, why is it nicknamed the Ring of Fire? And why do so many earthquakes originate in this region? So the answer to that previous question, the belt exists along boundaries of tectonic plates where plates of mostly oceanic crusts are sinking or subducting beneath another plate. Earthquakes within these subduction zones are caused by slips between plates and ruptures. The Alpine earthquake belt extends from Java to Sumatra through the Himalayas, the Mediterranean, and out onto the Atlantic. If you look at the picture, the Eurasian Melanesian belt is what we refer to as the Alpine belt. extends across Eurasia, and it is accounting for about 17% of the world's largest earthquakes following the Ring of Fire. The next most prominent belt is the Mid-Atlantic Ridge. The mid-oceanic ridge in the picture is what we were referring to. This marks where two tectonic plates are spreading apart as divergent oceanic plate boundaries. Most of the mid-Atlantic ridge is deep underwater and far from human development, but Iceland, which is directly over the mid-Atlantic ridge, has experienced earthquakes as large as 6.9. The remaining shocks are scattered in various areas around the world and are not as noticeable as these three. Next, we have natural disaster responses. This is for the United States, but it should be a pretty good frame of reference for the other countries. So when a disaster is declared, the federal government, led by the Federal Emergency Management Agency, or FEMA, responds. FEMA appoints a federal coordinating officer, or an FCO, and a Joint Field Office, or a JFO, to lead the response. They also organize a National Disaster Recovery Framework, or NDRF. They also appoint a Federal Disaster Recovery Coordinator. Recovery often begins while emergency response is still in progress. The NCRRSF could be activated by FEMA for all or some of the states. The NCRRSF could be activated by FEMA for all or some of the 6 stages of disaster recovery, depending on the NCR needs for particular disasters. These stages are listed below. So next we're going to talk about mountain formation. We have 3 main types of mountains: volcanic mountains, fold mountains, and block mountains. Sometimes you hear mountain formation referred to as orogenies. So first we're going to talk about volcanic mountains. This is when movements of tectonic plates create volcanoes. Volcanic arc systems is a series of volcanoes that form near a subduction zone where a crust of a sinking ocean plate melts. This is most notable in the Ring of Fire. The most important types of volcanic mountains are the composite cones and the stratovolcanoes and the shield volcanoes. So all but the domes. Examples of a composite or stratovolcano are the Vesuvius, the Kilimanjaro, and Mount Fuji. And the Mauna Loa is a prime example of a shield volcano. Next, we have the fold and block mountains. A fold mountain occurs when the plates undergo subduction or ride over one another, and the plates buckle and fold, which form the mountains. Most of the major continental mountain ranges are associated with this type of folding. Examples of the Jura and Zagros mountains. We have the block mountains, which occur when the fault is raised or tilted, and the block mountains can result. Higher blocks are called horsts, and troughs are grabens. A spreading part of the surface causes tensional forces, and then when the tensional forces are strong enough, they cause a plate to split apart so much that the center block drops down relative to the pushing flanking blocks. A prime example is the Sierra Nevada range, which creates 650. A prime example is the Sierra Nevada range on the top right corner, which has blocks over 650 kilometers long and is the highest mountain front in the continental United States. And the fold mountains, example you can see on the bottom right. The tectonic forces that lead to mountain building are continuously countered by erosion due to intensified precipitation, wind, and temperature extremes. So all the elements at work create an intense storm in the mountains. Some of these include gale force winds, lightning strikes, snow, hail, rain. They're sculpted forms that we see, and this occurs over millions and millions of years, but the amount of debris it creates, you can see in the picture on the right. More examples: falling ice, rocks, gushing water. They accumulate in valleys, and then they also flow down mountains as slow-moving glaciers, just huge masses of rocks. And when these melt with the ice, the piled rock debris are called moraines, and they leave behind scratches and grooves on the mountains. Sometimes lightning will even hit and vaporize the water and ice in rock fissures and then blow rocks apart. We also have temperature changes that thaw out and refreeze the ice. We also have rock falls and ice avalanches over mountain sides, which erode the slopes. We also have powerful earthquakes that are responsible for the uplift of mountains, as well as destabilizing them. which cause many rockfalls and avalanches to help wear them down. Summary: earthquakes are created differently through different waves, through different mediums. If you have a body wave, you can have the S or the P wave. And then with the surface waves, we have the love wave and the Rayleigh wave. Each of these waves do different things and look differently and move differently. We also have triangulation, the way you determine where the epicenter forms through 3 circles, and where these 3 circles interact is where the epicenter starts. We have 3 different types of mountains: volcano, folds, and blocks. Volcanic mountains are volcanoes. Fold mountains is your typical 2 plates coming together and crushing rock to form a mountain. The block mountain is where the plate actually cracks and the plate comes upwards. It creates like a block shape. We have erosion that constantly breaks down the mountain. And that's it. So for the next video, we're going to talk about structural geology, maps, and Earth's history. And I will see you then.